Next question is question number 45. In this question, it is given xt is a stationary process with the power spectral density given as S x of f, which is always greater than 0, that is always positive for all frequency. The process is passed through a system shown below. The xt process that is passed through a system which has a delay parameter, and after the summation there is the differentiator, then we get the output process y of t. Let Sy of f be the power spectral density of y of t, that is the power spectral density at the output y of t is given as Sy of f, and input power spectral density is given as Sx of f. Which one of the following statement is correct, that we have to see. If you see in the option, it is asking about the information about the output power spectral density, that is at what frequency it is becoming 0, if it is becoming 0, or else whether it is non-zero for all frequency f, that we have to see which one is correct. Now if you look at the question, here the input power spectral density is given, there is a system and output power spectral density is Sy of f, then we can get the output power spectral density Sy of f simply if we multiply input power spectral density Sx of f with the magnitude square of the system, that is represented in frequency domain, then we can get the power spectral density at the output. So once we get the power spectral density at the output, then we can find out the information about the power spectral density, that is when it is becoming 0 or whether it is always greater than 0, that we can find out easily. So first our aim is to find out the system transfer function in frequency domain, so that we can get the output power spectral density. Now let us represent the y of t, that is in time domain, as a function of x of t. Here if you see, x of t is added with the delayed version of x of t, that is x of t is delayed by 0.5 millisecond, both are added, and the summation of the signal is differentiated to get the output signal y of t. Let's say capital T is the delay, that is 0.5 millisecond. Then we can easily represent the output signal y of t, which is equal to differentiation of both the signal, that is x of t, and delayed xt, that is xt minus t. Okay, so y of t is represented like this. We can find out the Laplace transform of y of t, that is y of s, will be equal to this differentiation will be simply s x of s plus e to the power minus st, because of the differentiation s will come here, then x of s. So this is the Laplace domain. We can get the transfer function y of s by x of s will give us the transfer function. So y of s by x of s, which is equal to h of s, that is the transfer function, is equal to s plus s into e to the power minus st. Now let us replace this s as j omega, so that we can represent in frequency domain. So h of j omega will be equal to j omega plus j omega e to the power minus j omega t. Now e to the power minus j omega t we can represent in cos and sine function, because our aim is to find out the system transfer function magnitude, so that we can take the square of that and we can multiply with the input power spectral density to get the output power spectral density. So our aim is to represent this transfer function into real part plus j into imaginary part, so that we can find out the magnitude. So here if we expand this, that is e to the power minus j omega t in cos and sine function, then we can write like this: j omega plus j omega e to the power minus j omega t will be simply cos omega t minus j sine omega t. After further simplification we can get this expression. Okay, again after simplification we can separate the real part and imaginary part like this: real part plus j into imaginary part, because here real part is omega sine omega t, so omega sine omega t, and if you take the j common, this will be equal to omega plus omega cos omega t. Now what is the magnitude of h of j omega? Simply this square plus this square, the whole root over, or we can say h of omega magnitude whole square equal to omega square, this omega square sine square omega t plus this imaginary part, that is omega plus omega cos omega t whole square. Let us expand this one. then we can write like this. Here if you see, this is omega square cos square omega t, this is omega square sin square omega t. So omega square if you take common, then this sin square omega t plus cos square omega t, that will become equal to 1. So we can write 2 omega square, because this is omega square and these two terms also will give another omega square. So 2 omega square plus 2 omega square cos omega t. Further, if you take 2 omega square common, then we will have this expression. This is nothing but the transfer function of this total system. So we can get the output power spectral density Sy of f is equal to input power spectral density x S of f into h of f whole square. Here if you see, it is already given that the input power spectral density is non-negative for any frequency, because x of f is always greater than 0 for all frequency. So we have to see only at what frequency this magnitude is becoming 0, so that the output power spectral density will be becoming 0. So if you see, for the output power spectral density to be 0, this magnitude square has to be 0, that is this part has to be 0, and this part will be becoming 0 under two cases, that is when the frequency, that is omega equal to 0, or this part is becoming 0. So at the first case, if the frequency is becoming 0, that is f is becoming 0, then this part is becoming 0, then the whole part is becoming 0, so that the output power spectral density will be becoming 0. And in other condition, the other part, that is 1 plus cos omega t, if this part is becoming 0, then also the output power spectral density will become 0. So if 1 plus cos omega t is becoming 0, then the output power spectral density is also becoming 0. So if we simplify this, we can find out at what frequency the power spectral density is becoming 0. So this is nothing but cos omega t equal to minus 1. For this to become minus 1, omega t has to be odd integral multiple of pi, or we can say omega t is equal to 2n plus 1 pi. Simply, if we substitute omega is equal to 2 pi f, and this t is already given 0.5 millisecond, then we can find out at what frequency the signal is becoming 0. So after simplification, we got f equal to 2n plus 1, because millisecond is there, inverse of millisecond is nothing but kilohertz. If we represent f naught here, 2n plus 1 whole into f naught, and f naught is 1 kilohertz, that is f naught is equal to 1 kilohertz, then at this frequency also the power spectral density is becoming 0, or we can say at the odd integral multiple of 1 kilohertz the power spectral density is becoming 0, and also when the frequency is 0, the power spectral density is becoming 0. So if we analyze by taking n different integer value, that is 0, plus minus 1, plus minus 2, plus minus 3, then we can check at what frequency the power spectral density, that is the output power spectral density, is becoming 0. So at 0, simply at 0, if n equal to 0, then simply it is coming as f naught, that is 1 kilohertz, so 1k. If you take the plus 1 here, if you take the plus 1, then this factor will be equal to 3. So 3 f naught, that is 3 kilohertz, 3 kilohertz. For 2 it will be 5 kilohertz, for 3 it will be 7 kilohertz. Similarly, at the negative integer, that is minus 1, minus 2, minus 3, if we substitute in this expression, we can get the frequency as minus 1k, minus 3k, minus 5k. These are also odd integral of f naught. So at odd integral of 1 kilohertz, the output power spectral density will be becoming 0. Also at frequency equal to 0, the output power spectral density will become 0. Now let us check for the option. In the first option, it is given that output power spectral density is always positive for any frequency. So this is not true, because we have already found out at what frequency the output power spectral density is becoming 0. So A is not correct. Coming to the option B, in the option B, it is given that the output power spectral density Sy of f is equal to 0 for any frequency modulus which is greater than 1 kilohertz. If you see, at frequency equal to 0 also, the Sy of f is becoming 0, so option B is also eliminated. Next, coming to option C. In the option C, Sy of f equal to 0 at f equal to n f naught, where f naught equal to 2 kilohertz. Simply this is the condition which says the frequency is even integral of f naught, but we have already found out only at odd integral of f naught the Sy of f is becoming 0, so this option is also not correct. Coming to option D, it is given that Sy of f equal to 0 for frequency f is equal to 2n plus 1 f naught, where f naught is equal to 1 kilohertz, n is any integer. So option D is matching with our result. So option D is the correct answer for question number 45. Next is question number 54 and 55. Both are linked question, that is common data question. It is given that consider a baseband binary pulse amplitude modulated receiver shown below. This is basically the receiver that is given. The additive channel noise NT, this noise is added here, is wide with power spectral density is given as n0 by 2, 10 to the power minus 20 watt per hertz. That is the power spectral density of the AWGN, that is additive white Gaussian noise, is given. The low pass filter, that is the low pass filter, is implemented at the receiver, has an ideal characteristic with unit gain and cutoff frequency is given to be 1 megahertz. Let yk represent the random variable y of tk, where y of k equal to nk if transmitted bit bk equal to 0, y of k equal to a plus nk if transmitted bit bk equal to 1. What is nk? Where nk is represent the noise sample value. The noise sample has the probability density function, that is the probability density function of the sampled noise is also given, and it is also given that it has 0 mean and variance is equal to 2 by alpha square. It is also given, assume the transmitted bits to be equiprobable and the threshold Z is set to a by 2 equal to 10 to the minus 6 volt. Then we have to find out what is the parameter alpha. In question of 55 we have to find out what is the probability of bit error. So this is basically the pulse amplitude modulated receiver. The noise is added here. The summation of the signal is passed through a low pass filter, then the sample and hold circuit will sample the signal yt. Then the threshold detection to detect the bit as 0 or 1 as per this logic, that is the logic is this, which is saying the bit will be treated as 0 if at the output the amplitude is nk, and the bit will be treated as 1 if at the output the amplitude is a plus nk, where a by 2 the threshold is given to be 10 to the minus 6. So what is given is the transfer function of the low pass filter has a unit gain and it is also ideal, that is it will have a sharp cutoff frequency and the cutoff frequency is given to be 1 megahertz. So we can get the noise power spectral density at the output, because noise power spectral density at the output is simply the noise spectral density, that is input to the low pass filter into h of f magnitude square. So PSD 0 is equal to Sn of f, that is Sn of f is given, and h of f whole square. Magnitude of h of f is already 1, so we can get the output power spectral density. Then the noise power is nothing but integration from minus infinity to infinity of the output power spectral density, that is PSD df. Here the integration limit will be simply restricted to minus 1 megahertz to 1 megahertz, because the low pass filter has a sharp cutoff frequency. So the integration limit will be from minus 1 megahertz to plus 1 megahertz, and Sn of f is simply n0 by 2, that is equal to 10 to the minus 20 is already given. So 10 to the minus 20. So after integration of this, we will get the noise power to be equal to 2 into 10 to the minus 14 watt. This is the noise power at the output. If you see, the noise probability density function is given in the question, and it is also given that it has 0 mean and variance is 2 by alpha square. As it has 0 mean, so the variance will be representing simply the power of the noise. So this 2 by alpha square will be equal to the noise power. So as I have said, as the noise has 0 mean, hence its variance will be representing the noise, simply the noise power. So if we equate this 2 by alpha square, that is the variance, with the noise power, then we can get the value of alpha to be 10 to the power 7 volt inverse. So in the question number 54, the option B is giving the right value of the alpha. Hence option B is correct for question number 54. Next part, that is question number 55, we have to find out the probability of bit error. To find out the probability of bit error, we have to draw the decision line first. Let us say at this point it is nk and this length is a, so that at this point the amplitude will be nk plus a. Okay, because at nk plus a the bit is exactly detected as 1 and at nk the bit is detected as 0. It is also given that the threshold z is simply is equal to a by 2, which is given to be 10 to the minus 6 volt. So the threshold will be exactly at the middle of this, which is equal to a by 2. As per the decision logic, when at the output amplitude is varying around nk but it is not exceeding the value of a by 2, then at the output the bit will be treated as 0. Similarly, for bit to be treated as 1, for this part the bit will be treated as 1, that is when the output y of k is varying around nk plus a and it must not exceed the value of a by 2, then the bit will be treated as 1. Then what is the probability of error? The probability of bit error is simply probability of 1, that is the probability when 1 is transmitted, that will be multiplied with the conditional probability, that is when 1 is transmitted but at the receiver it is detected as 0, that will be added with probability of 0, that is probability when 0 is transmitted, which will be multiplied with conditional probability, that is 0 is transmitted but at the receiver we got the bit as 1. This is the probability of bit error formula. As in the question it is given that the transmitted bits are of equiprobable, that is probability of transmitting 1 and probability of transmitting 0 are equiprobable. As there are only 2 bits, so each probability will be simply 1 by 2. So we can substitute that probability of 1 is equal to 1 by 2, and next the conditional probability plus probability of 0 will be equal to 1 by 2 into probability of 0 is transmitted, 1 is received at the output. Now we have to find out this conditional probability and this conditional probability, then we can get the probability of bit error. Here we have taken simply half as common, then we can express the probability of error in this form. First let us find out this conditional probability, that is when 1 is transmitted but we got at the receiver as 0, or we can say error when 1 is transmitted. If we see this amplitude line, then when actually this error can occur, because here 1 is transmitted but we are getting 0, that means the output yk when it is coming below a by 2, because when bit 1 is transmitted and because of the noise this point is fluctuating so that it crosses this a by 2, that is when yk is less than a by 2 the error will occur. Okay, so when yk is less than a by 2 this conditional probability of error will occur, and for 1 to be transmitted, that means a plus nk is transmitted, so we will substitute yk as a plus nk. So a plus nk is less than a by 2, that means nk is less than a by 2. Then we know the probability density function as it is given in the question. So if we integrate this from minus infinity up to this point, then we can get this conditional probability. So probability of 1 is transmitted and 0 is received will be equal to minus infinity to a by 2 up to this limit it is integrated, and this probability density function will be there. Here as modulus of n is given, So it will be simply n, because its power will be always negative whether n is positive or negative. So here as n is negative, if we substitute negative, it will coming as minus alpha. So the expression will be simply e to the power alpha n for negative value of n. So if we integrate this, we will get 0.5 e to the power minus 10. So we got this conditional probability value, that is probability of 1 transmitted, 0 is received. Next we can get the conditional probability when 0 is transmitted and we received 1 at the output. So what is this conditional probability? This conditional probability is nothing but error occur when 0 is transmitted. That is 0 is transmitted because of the noise. This point fluctuates so that it crosses a by 2. So error will occur when the yk is greater than a by 2. So if yk is greater than a by 2, the error will occur, and for 0 to be transmitted, yk is simply nk. So nk is greater than a by 2. Again we will integrate that PDF probability density function for positive value of n. For positive value of n, simply minus alpha n will be there at the exponential part. So the probability of 1 by 0 will be equal to a by 2, because nk is greater than a by 2. So the integration will happen from a by 2 to infinity. That will be integration of the probability density function in respect of dn. If we integrate this, we will get the value to be 0.5 e to the power minus 10. We have also got same value for this conditional probability. As both values are equal, so you can say half into 2 times 0.5 e to the power minus 10. So this will be simply equal to 0.5 e to the power minus 10. That is the probability of bit error asked in the question. So if you see, option D is matching with our probability of bit error. Hence option D is the correct answer for question number 55. This concludes solutions with concept of all the questions of GATE 2010 in respect of communication subject. For solutions detail of others year question, you may scroll through my channel Helping Hand for EC Student, or you may follow the below mentioned link to find out solutions of others year questions. If you like, you may subscribe to my channel Helping Hand for EC Students to stay updated with latest videos showing concept wise solution detail of previous year questions, which will be again based on subject wise. If you have any query, you can always drop your comment in comment section. I will address your query. Thanks for watching.